12 Physics, the end of week 3 check-in. I know some of you have had some trouble with these, so I'll just run through them. So first question is, an object is rotating at 1200 hertz. That means that it's doing a full circuit 1200 times per second. So hertz is always per second. So it's doing 12 laps around. So it's going really, really fast. And here this bears that out. It's going 2.5 by 10 to the 3 meters per second. And the question wants to know what the acceleration is, because when anything goes in a circle, right, even though the velocity is constant, so if I've got something going around here in a circle and it's going at 2.5 by 10 to the 3 meters per second, the velocity can be constant. Or not the velocity, the speed can be constant. And it actually says that in the question, speed, not velocity. But because as it goes around, its direction is changing, that means that its velocity is changing. And if it's changing its velocity, there'll be acceleration, there'll be an unbalanced force acting on it. So we're asked to find the acceleration. So the formula for finding acceleration is usually this one, v squared on r. But I've got the v, I don't have the r. So I've got to get this r from somewhere. So if I have a look through my formulas, I'll find there's a formula, v equals 2 pi r on t. T stands for period, and period is how long it takes you to do a circuit. So it's actually the reciprocal of frequency. So you needed to have this couple of little bits of extra knowledge that you hopefully had picked up as you went through. So frequency is 1 on t. So I could rearrange that formula to be 1 on t times 2 pi r. Or I've substituted in frequency is 1 on t. Frequency equals by 2 pi r. So I put the 1t in front and then I changed it to f. I could have left 1t out the front there. It wouldn't have mattered. I substitute in. I've got my radius now. That will be in meters. Put that back into this formula that I wanted to work with in the first place, and I get the acceleration is 1.9 by 10 to the negative 7. Now, that seems really fast. Remember, yeah, it was going really fast, so that's okay. That's all right. Now, acceleration should have a direction. So it's actually, the force is acting inwards to the center. So that's the direction. So it's 1.9 by 10 to the minus 7 meters a second towards the center. All right. All right, next one. We've got a car on an incline and it weighs 1,000 kilograms. It's sliding down an icy frictionless incline at 15. The incline is 15 degrees. It says work out the acceleration. So if it's sliding down here, this is the net force on it because there's no friction. This is going to be our F net. And of course, F net equals MA. Right, so the net force is the one that produces the acceleration. So this is the force, the component of the weight that's going down the slope. So I need that component. I don't need the normal force or any of that. So I need the weight, FW equals mg. So that's our weight. Remember, this angle and that angle are the same. Sine of that angle, opposite over hypotenuse. So the parallel force over the weight. So F parallel is FW sine theta. That gives me the component of the weight that's acting down the plane. That's going to be my net force. Divide that by the mass to get the acceleration. And again, acceleration is a vector quantity, so we should have a direction down the slope. That's something that we have to be careful of so that we make sure you get your maximum marks in the exam at the end of the year. Right, question 3 is similar, only this time there's a little bit more information hidden in it. So it says that it is sliding at 3 meters per second, so it's got a constant velocity. So if there's a constant velocity, that tells me that there's no net force. So these two forces must be balanced. There's no acceleration. It's a constant velocity, no acceleration, no net force. These two forces are balanced. And I'd want to see a sentence somewhere or some indication that that's the principle that you're going to use. All right, so again, we need this. We need the weight from the mass, so mg, and we want that component down the slope because force of friction is going to be equal to it. So it's the same as before. The force parallel is equal to the weight times sine theta. So that gives me the force down the slope. Right, so the force of friction is going to be equal to that, but up the incline. Don't forget, put your direction in because it's a vector. Righto, this question here was a bit tricky. An object of mass 2.5 kgs is whirled on the end of a 75 centimetre long string in a vertical circle at constant speed. The string will break if the force exceeds 200 newtons. How fast can the object be whirled before the string breaks? So I've given you the hint there that you need to do the drawing, and you'll notice I've done a drawing of all of these before I started and mark in all the forces. So as the object comes down here, it has the tension in the string and it also has its full weight when it's here at this bottom point. That's going to be where the maximum force occurs. And you know that yourself. If you're twirling something around, you can do it with a piece of string, you can do it with a bucket with some water in it. You will feel that there is more force required when it's at the bottom there to hold it. So we've got to this string has got to overcome that weight, and it's also got to put up with the tension from the centripetal force. Right, so at the bottom of the string there, you've got this, at the bottom of the circle, you've got the centripetal force and you've got the weight. So they can only add up to a maximum of 200. So we get the weight. What's that? 24.5 newtons. I'm going to take that off the maximum that the string can bear, 175.5 newtons. That's the maximum tension that I can have in the string from the centripetal force. Then we're going to go and put that into the centripetal force formula to work out the maximum speed that the object can be twirled at. It's a 2.5 kilo object, so it's going to be pretty deadly if that string breaks. And you can swing it at 7.26 meters per second. Right, the object swung no faster than that. That's the maximum. At that point, you've got 175.5 newtons of force in the string from the centripetal force, and you've got the weight of 24.5, which adds to 200.